Assalamualaikum warahmatullahi wabarakatuh, and a very good day to my very respected dear panels. Panel 1, Associate Professor Dr. Zulkifli bin Mohamad Rosli, and Panel 2, Puan Nur Irina binti Omar. My name is Mohamad Hazzim bin Muhammad Anuar. I am from 4BMMP Section 11. Today, I am going to present my final Bachelor Degree Project 2 on the title of Surface Integrity and Wear Mechanism H13 Tool Steel Machinability Assessment. Before I begin with my presentation, allow me to introduce my supervisor, Associate Professor Technologist Dr. Umar Al-Amani bin Haji Azlan, and my co-supervisor, Technologist Dr. Nur Fauzi bin Tamin. For introduction, I am going to briefly explain about three main aspects, which is number 1 is the H13. H13 is a tool steel that can resist the thermal fatigue, abrasion and wear. Number 2, surface roughness is abnormalities that occur usually after manufacturing process. And number 3, tool wear is a regular operation of cutting tool that causes tool to degrade or fracture gradually over time. The problem statement of this research is the lack study of machining parameters, particularly on wear mechanism and surface integrity of H13 tool steel. There are several objectives in this research. Number 1 is to study the machining parameters that will be set up at the CNC machine, and number 2 to study wear mechanism and surface integrity by using tungsten carbide cutting tool. Surface roughness and tool wear are very related factors which involve in machining process. According to Ozel Kapat of 2005, has stated that surface quality in part machining are among the most well-defined, and surface roughness on machine part is a crucial component in determining surface quality. According to Atanasio et al. Of 2006, has stated that it is very serious issue to avoid productivity losses caused by excessive tool wear or breakage. In this research of methodology, there are going to be few lab process involved. And the first thing first, we need to prepare the material by using CNC machine. All the provided parameters of cutting speed, feed rate, depth of cut will be set up at the CNC machine. And as you can see for picture number 2, that is the real and exactly condition of H13 material. We need to cut the material into 8 stairs because one level of stairs for one surface roughness and cutting speed. The total of parameters will be 8 cutting speed. After all the process of machining is completed, we will take the sample of H13 to surface roughness lab. In this process, we are going to obtain the result of surface roughness by using surface roughness tester, and the model is SJ Mitutoyo 410. After surface roughness process is completed, we are going to analyze the tool wear by using optical microscope and scanning electron microscope. Both of these instruments have the same function to display the tool wear of cutting tool, but the only difference between optical and scanning electron is much more advanced because it can display the real microstructure of the tool wear compared to optical microscope, because optical microscope can only display the physical appearance of the tool wear. At the same time, we are going to analyze the surface roughness of H13 by using SEM. So this is the data result of surface roughness. I split it into 2 tables for the first parameter of 0.05 mm per revolution and 0.10 mm per revolution. As you can see, the surface roughness or deviation graph for 0.05, first feed rate, the peak is quite smaller for each cutting speed compared to second parameter. We can see that obviously the graph is quite bigger and quite large compared to first parameter, and it is clearly shown that the surface roughness for second parameter is quite rough than first parameter. This is the exact condition of surface roughness under scanning electron microscope. There are 4 cutting speeds and 2 feed rates. And I combine all the feed rate photos in one cutting speed so that easily to make a comparison. So for the first cutting speed of 100 m per minute, at 0.05 you can see that there is a oval shape and the toolpath is not clear because the surface roughness is quite lower. But when it comes on 0.10 mm per revolution, you can see that the surface is started to rough. The toolpath, we can see it very clearly, and there is a small spot of melted area. So this is caused by grain from H13. When machining, when it high temperature, it melt, which is why that the surface have some spot of melted area. For second cutting speed of 140 m per minute, you can see that the toolpath is not clear because the surface roughness is smooth, but there is a chip formation. Compared to 0.10 mm per revolution, we can see that the toolpath is very clear and there is a smearing occur. Smearing is like a valley, like a long valley occur along the surface, and it is caused by the same issue of H13 grain particle of H13 is melted when the process of machining is performed. For third cutting speed of 170 m per minute, for both diagram we can see that a sort of chip melted. Chip melted happens because it is attached in between H13 and material. When the stylus is moved, the chip is colliding with the material and causes the chip to melt. And finally, for final cutting speed of 200 m per minute, we can see that the surface is very smooth. For first feed rate, according to theory, increase in cutting speed but low feed rate will produce a lower surface roughness. Next, for the optical microscope, I listed into 2 tables for first parameter of 0.05 and 0.10 mm per revolution. So every cutting speed and all the images are formed in this table. Only there is not many analysis can be done because as you can see, the picture of optical microscope only shows the physical appearance like shiny surface of the toolware. It's like almost the same with every cutting tool. But we can proceed to later on at the SCM or scanning electron microscope. This is the overall images of toolware under scanning electron microscope. I split it into 2 tables for the first feed rate and second feed rate. But for this part, there is still no analysis can be made because the magnification is only 20 times of magnification. The exact microstructure can be shown once we proceed to the 100 times magnification. So this is the overall images of toolware under scanning electron microscope for 100 times magnification. We will discuss about first feed rate. For the first cutting speed 100 meter per minute, we can see that there is no defect occur and the abrasion mark is very consistent. Second cutting speed 140 m per minute, we can see that there is a flake mark at the top view and at the front view, and there is a notch as well. Flake means the coated layer of cutting tool is pulled off. According to Journal Tamin of 2020 has mentioned that flake formation is caused by resistance of chip which is connected to cutting tool, and that is why the coated layer is pulled off during the machining. What about notch? We can say that the position of the wear is very close to upper level of each cutting tool. If it occurs at the area, we can say that it is a notch. For third cutting speed 170 m per minute, we can see that the flake mark is also occur due to increase of cutting speed. The toolware started to pull off, like the flag mark. For fourth cutting speed of 200 meter per minute, we can see that the aberration mark is not consistent due to the height of cutting speed. Next, for second feed rate of 0.10 mm per revolution. For first cutting speed, we can see that there is a flaking mark as well at the top view. Flaking mark can cause from other reasons as well. And one of the reasons is when the formation of chip and pressure accumulate at the same spot, it will corrode the coated layer of cutting tool. Second cutting speed, we can see that there is very obvious defect at the edge cutting tool. So due to the increase of cutting speed, the chip formation rotate together along with H13. So since this is a wet condition, the coolant cannot direct pass through to the surface, and which is why there is some iron melted at the cutting tool. For third cutting speed, we can see that there is a coated layer is pulled off as well. Same goes with first cutting speed. And final cutting speed of 200, the aberration mark is very consistent and the tool wear is not bad as before or other cutting speed. This maybe possibility can cause from many factors. Since this is a wet condition, maybe at this cutting speed, the coolant can direct pass through to that particular surface, which is cause the tool wear is very good and very better condition. So this is the graph of surface roughness for both parameter of 0.05 and 0.10 mm per revolution. As you can see, the pattern for first feed rate shows an inconsistent value of graph, while at 0.10 mm per revolution shows an increasing pattern of graph. In a summary, we can say that, and most probably, this kind of feed rate 0.05 is not matched with the cutting speed provided. Maybe some of the cutting speed is matched, but there are some of the cutting speed is not matched. For 0.10 mm per revolution, the graph pattern is very increasing from low to high, and this is very according to theory from Journal Tamin of 2020, has stated that the higher the feed rate will provide a higher surface roughness. So this is the graph analysis of tool wear for both feed rates 0.05 and 0.10 mm per revolution. According to the first graph of first feed rate, it shows a great consistent of decreasing in terms of its tool wear from 100 to 170, but not at the cutting speed of 200 m per minute. This can be concluded or summarized during the surface roughness testing. For that particular surface of 200, maybe the surface is interrupted by another particle or small particles that might affect the reading as well, which is why you can see that the cutting speed of 200 m per minute is not accurate. For second feed rate 0.10 mm per revolution, for the first cutting speed and second cutting speed, the value of tool wear is decreasing. But when it approaches to 170 and 200, the tool wear increases at a normal rate. This can be summarized by a factor of coolant. Since this is a wet condition, there is a possibility for this cutting speed 170 and 200, the surface receive an enough coolant flow, which can be helped to reduce the temperature of spindle speed, and that is why the reason the tool wear is not decreased but increasing or in a good condition. There are three conclusions that can be summarized in this research. First thing first, the provided machining parameter of cutting speed 100, 140, 170 and 200 m per minute, and two feed rates of 0.05 and 0.10 mm per revolution are suitable parameter for machining H13 under wet condition. Secondly, the result shows that the data obtained of feed rate 0.10 mm per revolution is much better than 0.05 mm per revolution for H13 material. And finally, each cutting speed on a different feed rate will provide a different effect and result. And possibility the slightly error can cause from many factors such as human error, machining factor or coolant factor. This is the references from previous journal. Before I end my presentation, I would like to express my special thanks of gratitude to Associate Professor Dr. Zulkifli bin Mohd Rusli and Puan Nur Irina binti Umar for spending your time on my presentation day. Until next time, take care. Assalamualaikum warahmatullahi wabarakatuh.